Hello and welcome to section 5.4. We're going to be talking a little bit about polarized light and how to determine not only the specific rotation for a molecule, in other words, how much a molecule rotates light, but also how to determine the enantiomeric excess or purity of a mixture of compounds. Now, um, your book has a nice little example of what plane polarized light is. And in plane polarized light, you have some molecule, such as this R carbone, or maybe this S carbone, that is actually able to change the rotation of light. So if you remember from beginning physics, light has an electric field part and a magnetic field part. And if you were to try and visualize the light coming from the sun, perhaps, you would see that all of the electric parts of the light can have all different directions, and it's totally random, and there's no orientation to this light at all. That means that all types of electric waves are coming through. But you could align this, or you could change the light that you're observing to what's called polarized light. And polarized light, or plane polarized light, is the type of light that is more or less selected for one type of direction. So that means that even though it's still light and it still has brightness and it still has a color, just like we observe with other light, it only has a single plane of light that you're actually observing. It's kind of a weird thing, and it's still hard for me to wrap my head around this idea of light looking the exact same, but physically, in physics terms, having only one type of light coming through. It's a weird one. And to have a nice little visual representation of this, you can see that in a case where you have all types of polarized light, and then you select for maybe just the vertical plane polarized light using the slit, this series of slits that is vertically oriented, shown here. It allows the vertical light to pass through, and if you were to observe this through the same slit with the same orientation, you would see the light coming through. However, if you were to look at now the light being selected for the vertical light, but then the plane polarizing slit that you're looking through is not oriented vertically, but instead oriented at a different angle, you won't see any light because of the polarized nature of that light. So we can measure actually the angle that vertical light is rotated by a chiral molecule, because something kind of weird about chiral molecules is that chiral molecules can take vertically oriented light like this, and just simply by passing, or by the light passing through the molecule, it can rotate it. And those are called optically active molecules. Um, those are called optically active molecules, and they're the ones that cause um, light passing through the slits to seem to be rotated. Now, I'll go back to the book real fast before we move on, because I want to show you a device that's used to determine um, the optical rotation of a sample. And this is called a polarimeter, which is a very simple idea. So imagine that you have light, say from the sun, and it goes through a polarizer to make that vertically oriented light that we just talked about. Directly after that, the light passes through a sample of some molecule dissolved in a solvent. So now this molecule has some chirality maybe, and because of that chirality, it changes, it rotates the light by some definite degree. So then us, the scientists, would be on the other side of the tube, and um, we would have a similarly polarized light filter, and we could simply twist this filter until we determined how many degrees of twisting we need to do until we saw light again. And simply by recording this value, we can get an idea of the optical activity of a molecule, or how much, how strong the light rotation is for that chiral compound. And for a nice little cool history lesson, you can read in your book 5.4 about Louis Pasteur and how he invented this as well. Okay, so let's look at the notebook real fast, because there are a couple ways we can describe this light rotation. First is in specific rotation, which means intrinsically to each molecule, each chiral molecule, how much should that light be rotated. Additionally, there's also an observed rotation, because the specific rotation is measured at standard values, but often we aren't doing our measurements in standard conditions. So because of that, we observe, or we have an observed rotation, which is specific rotation, but totally dependent on our own experiments. What does that mean? I think it's best to look at the math behind it to see what that means exactly. Because specific rotation is the absolute value of alpha, okay, there, but it is it, it is also equal to the observed rotation in the proper conditions. An observed rotation is equal to the alpha that you observe in an experiment over the concentration. Let's do this in red. C is the concentration of your molecule in moles per liter, or molar, and L is how long that polarizing tube was. So we call this the path length, often in centimeters. So we can describe the observed rotation at a certain temperature, and at a certain wavelength of light, because the amount of rotation changes depending on the type of wavelength that you're using, to give us a rotation that we can write and tell others about, to communicate the specific rotation or the observed rotation of a molecule. Okay, and something kind of cool is that if you have two enantiomers, they will actually rotate light the same amount. That is, their specific rotation should be the same amount, and at a certain at the same concentration and the same path length, their observed rotation should be the exact same in magnitude, let's say plus 100 degrees, but should be opposite for the other enantiomer. There should be 100 here. So it's kind of a cool thing about enantiomers. They rotate light at the same magnitude, but opposite values. And you can determine the amount of enantiomeric excess you have, that is, how much more of one enantiomer do you have than the other, by using the simple formula for enantiomeric excess shown in your book on page, where is this? It is on page 198 in 5.4, where the percent enantiomeric excess is equals to the observed, the absolute value of the observed rotation, alpha, over the alpha you expect for a pure enantiomer, and that's the absolute value again, all times 100 because it's a percent. Um, so if something has only one enantiomer, it's called enantiomerically pure. But if there's a 50-50 mix of both enantiomers, both R and S, it is called a racemic mixture. All right, a couple weird things about enantiomers and optical activity. There is no correlation at all between R and S and whether they rotate positive or negative. It's really weird, but there's no correlation there at all. Two different R molecules um, can rotate light in positive or negative. It doesn't matter. The magnitudes also typically are very hard to predict and so don't usually correlate. And in addition, if you have a racemic mixture, you don't have any optical rotation because one enantiomer rotates, a certain strength one way, and the other one, being 50%, rotates it all the way back to zero the other way. Um, yeah, so I think that's what you need to know about section 5.4.